Good morning, everyone. My name is Kai Fu. My topic is MILP-based automatic search algorithm for differential and linear trails for Speck. I worked with Wang, Guo, Sun, and Hu. Sorry. At first, I introduced the existing automatic search method for differential and linear trails based on MILP. The first, at 2011, Moha and Wu et al. Proposed the method to search the minimum differential active S boxes with MILP server. In Asia Crypt 14, a general heuristic automatic search algorithm is given by Sun et al. Then Sun et al. Transformed the heuristic method to a non-heuristic algorithm method. Next, I give a brief description of progress of such automatic algorithm for differential and linear trails for AIX ciphers. The automatic search method for differential in AIX-based hash function is provided by Laurent, Mendel, and Richburg et al. In CTISA 14, Bayukov proposed the threshold search method. In FSE 15, the Bayukov et al. Given an automatic method for best differential and linear trails in AIX ciphers. There are two reasons to motivate us to study the MILP-based method. The current MILP-based method cannot be applied to AIX ciphers. Before FSE 16, there is no general method for linear trails for AIX ciphers. Our contribution is that we propose the MILP model to search for differential and linear trails and Markov assumption. We applied our model to Speck and improve the attack on Speck with block size greater than 32. At first, I introduced our method to construct the MILP model for differential characteristics of module addition. We use the Lippmann and Maria's words to work to judge the differential is possible or not. Let the two input difference of modular addition be alpha and beta. The output difference is gamma. If the all differential alpha beta to gamma is possible, the alpha O or beta O or gamma O must be empty. Another constraint is that if alpha I minus 1 equals to beta I minus 1 equals to gamma I minus 1, the alpha I or beta I or gamma I must be alpha I minus 1. This is a simple example. In addition, Lippmann and Maria also given a simple method to calculate the all differential probability. They found that the probability is related with the equation function. The equation function is defined as this. If alpha I equals to beta I equals to gamma I, the equation function is 1. Otherwise, it's empty. This is a simple example. We can fast calculate the probability. Next, I introduce our method to construct the MILP model for modular addition. At first, we use 5 linear inequalities to satisfy the first condition: alpha O or beta O or gamma O is 0. This is 5 inequalities. Next, we use the vector alpha I, beta I, gamma I, alpha I plus 1, beta I plus 1, gamma I plus 1 to donate the relation of differential values for ith difference bit and the ith plus 1 bits. From the first theorem, we can know that the vector is only 56 possible pattern, not 26. From the second theorem, we know that the probability is only with the equation function. So we add the equation equal function to the vector to compute the to calculate the probability efficiently. At last, we use the Sage in www.sagemath.org to generate the linear inequalities to construct our model. Here we give the example to how to use the Sage to generate the inequalities. This is the example to generate the inequalities satisfy the differential property of all opposition. At first, we input the possible pattern. Then we use the inequality generator function to generate the inequalities. In order to speed up our search procedure, we use the greedy algorithm given by Sun et al. To reduce the number of inequalities. At last, we get the 13 inequalities to donate the differential value, the relation of the differential values for the s and the s+1 bits. Besides the modular addition, the OR operation, the three-forked branch operation, and the circular shifted operation also involved in AIS ciphers. We next construct the MILP model for these operations. For bit level operation A or B is C, we can use these 5 inequalities to satisfy their property. For three-forked branch operation, we let the input difference are A and B, the output difference is C. So we can list the equation A equals to B equals to C to satisfy their property. For the circular shift operation, we only list the equation for the related bits. Now we can construct the MILP model for differential characteristics of AIS cipher. However, there are some restricted conditions in our model. We only consider the modular addition with 2 inputs. And we assume the 2 inputs and the consecutive round are independent. However, due to the dependency issues, the practical probability of our identified differential characters may vary from that derived from our model for some fixed k. Next, I introduce the method to construct the MILP model for linear approximation. We use the Warren and Nyberg's work to calculate the correlation of linear approximation. Let the 2 input masks be gamma alpha, gamma beta, the output mask tau. So we can use this formula to calculate the correlation, where the L is a row vector, the C is a column vector, the AR is 8 2 times 2 matrix. The mu is the n-bit vector, where mu I can use this equation to calculate. This is the simple. This is the example. In addition, the Nyberg and Warren also use the automaton to calculate the correlation fast. They define the state EO is L and E1 is O1. Then they found the law. We can use this picture to donate the law. The start state is EO if the mu I is O, the next state is also EO. If the mu I is mu 7, the next state is E1. If other is empty. This is the example. So from the opposition, we get the proper position. If the correlation is non-zero, the absolute value of the correlation is the number of the occurrence of state E1. We also use the picture to donate the state transition. Under the start state is EO, and under the mu I, from the state C I plus 1 to state I. There mu can use this equation to calculate. We also introduce a new variable si. If the I is EO, the Si is O. If the I is E1, the Si is 1. So we use a similar method to construct our MILP model. We use the vector Si plus 1, tau I, gamma alpha I, gamma beta I, Si to denote the state transition under the mu I from state ESI plus 1 to ESI. We should notice that the start state is EO, so we should add the additional constraint Cn is EO. At last, we also use the Sage and Grady algorithm to get the linear inequalities. We get the 8 linear inequalities. For other operations of AIS ciphers, we can construct the MILP model. For the 3-forked branch operation, we let the input mask be A and B. The output mask is B, C. So we can use the 5 linear inequalities to satisfy their property. For all operations A or B is C, we list the equation A equals to B equals to C. For the circular shift operation, we only list the equation for the related bits. Now we can contrast our MILP model for linear approximation. There are also some restricted conditions in our model. We only consider the modular addition with 2 inputs, and we assume the 2 inputs and consecutive rounds are independent. So due to the dimension issues, the practical correlation of our identified linear trails may vary from that derived from our model. At last, we apply our model to the Speck cipher. Speck cipher is proposed in 2003 by NSA. It's simple and is simple and usable for a variety of platforms. The parameters is listed in the table. It's 10 variants. This is the round function of Speck. There are 2 steps in our search procedure. The step 1 is generate the linear inequalities and convert the terms into a format that is readable by Groovy. The step 2 is use Groovy to search the trails with the input from step 1. Our code is published in the GitHub. Other MILP optimizers such as C++ also can also be used to solve our model. This is our result. From the table, we find the better differential and linear trails for Speck with block size greater than 32. We also use the Dyner's worker to attack the Speck cipher. This is our result. From the table, we can know that we improve the attack on Speck cipher with block size greater than 32. In this paper, we proposed the new MILP model to search for differential and linear trails for AIX ciphers. We applied our model to Speck cipher and improve the Speck cipher and improve the attack on Speck cipher with block size greater than 32. That's all. Thank you.